This video is covering section 6.5 about related rates, and that starts on page 82 of your course notes. It says often related rates are rates of change with respect to time. So dx dt, dr dt, dA dt, etc. So dA might represent area, dr might be the change of radius of a circle, for example. So our first example says a particle is moving along the circle x squared plus y squared equals 1, and its rate or velocity is in the x direction is dx dt equals 4 centimeters per second. What is the rate in the y direction, dy dt? Assume both x and y are differentiable functions in terms of t, so differentiate the equation implicitly like we did in the last week's work, with respect to t. So we're differentiating two different variables, x and y, with respect to t. So when we take the differentiation, or we differentiate this equation, we would get 2x, derivative of x with respect to t, and then 2y, and derivative of y with respect to t. So just like in the last section, if we found the derivative of x with respect to y or y with respect to x, we're doing the same thing, except neither of these variables are what we're differentiating with respect to. So we include the variable with respect to t. Now, we are given the velocity in the x direction, dx dt equals 4. We want to know what is the rate in the y direction. So really what we're looking for is dy dt, so we want to solve for this. So in order to do that, first we want to subtract 2x dx dt from both sides. And then we will divide both sides by 2y. So dy dt equals negative 2x dx dt, all divided by 2y. Now, we can cancel these 2's, and we can plug in this dx dt in instead of trying to simplify it. So we would get negative x times 4 divided by y. So finally, dy dt equals negative 4x over y. And of course, x and y are still left, and that's totally fine. Okay, so our change in y with respect to t depends on where we are at in the circle. Okay, so if a point on the circle would have been given, a specific value would be the answer. So if they wanted to know at a x and y coordinate, we would just plug in those values for x and y. But of course, in this example, they don't give us any more information. So the next example says, assume x and y are functions of t, evaluate dy dt for 8y cubed plus x squared equals 1. We're given dx dt, and we're given x and y values this time. So again, we just start out with differentiating the equation. So we're differentiating 8y cubed plus x squared equals 1. So we get 24y squared. And of course, we include dy dt, derivative of y with respect to t, plus 2x dx dt equals 0. And now it's simply substitution. So for dx dt, we're plugging in 2. For x, we're plugging in 3. And y, we're plugging in negative 1. So we could, if we wanted to, first solve for dy dt, but in my opinion, instead of doing that algebra, it'd be easier to plug in all of these values first. So y is negative 1, dy dt is what we're solving for, we don't know. X is 3, and dx dt is 2. So negative 1 squared is just 1, so we have 24 dy dt plus 12 equals 0. So we can subtract 12 from both sides, and then we can divide by 24, and we will get negative 1/2. And that is our final answer. Part B gives us an equation that has the natural log of x. So we have y, natural log of x, plus x e to the y equals 1. And then we're given dx dt, x equals 1, y equals 0. So the instructions are the same. We want to evaluate dy dt. Now, in this case, we do have to apply the chain rule, right? We have a product y times natural log of x, and then x times e to the y. Okay, so when we do this, we would have the first term times derivative of the second, so derivative of natural log of x is 1 over x, but then we also have dx dt plus the second term times derivative of the first. Derivative of y is just 1, but we would include dy dt. And then the same thing for our other terms. So then we would have x times e to the y. So derivative of, or first term times derivative of the second. Derivative of e to the y is just e to the y, but we do include dy dt. And then derivative of the first term is 1. The derivative of x is 1, but we must include dx dt. And derivative on the right-hand side of the equation of 1 is simply 0. So we have this long equation. So we can either solve for dy dt first and then plug in our values, or just go ahead and plug in our values. And it's probably easier to plug in what we have first at this point. So plugging in y is 0. This whole term is just 0, right? 0 times anything is 0. Plus natural log of x would be natural log of 1 times dy dt is what we don't know. That's what we're looking for. Again, x is 1. Then we have e to the 0, which is also 1. Dy dt, again, that's what we're solving for. E to the y again, so e to the 0 is just 1. Dx dt is 5. So if we simplify this, we have natural log of 1. We could factor out a dy dt from each of these terms, right? We have one here, and then I would subtract this 5 over to the right-hand side. E to the 0 again is 1, so 1 times 5 is 5. We subtract it from both sides. So if we factor out a dy dt, we're left with natural log of 1 plus 1 times e to the 0 is just 1. So then lastly, we would just have to divide both sides by natural log of 1 plus 1. Now, we also know that the natural log of 1 is 0, right? What this is, remember, a natural log is basically asking the base, e to what power equals 1, and that would be 0. So in short, dy dt is simply negative 5. Okay, now the next part of this section, we want to apply these to real-world problems, application problems. So there's some short steps in order to do this. Of course, you don't really necessarily need to follow the steps, but it can be helpful, especially if you get stuck. So first step would always be to read the problem and determine what we don't know. Okay, a lot of times I will draw a sketch of these problems, and then you have to label your variables if you're not given them, and determine what are we looking for. Often we're looking for the change, dy, dt, or something like that. Write your related rate equation. So we're going to write an equation with the information given, and then we're going to differentiate both sides, generally with respect to time for the problems we're going to do in this course. And then solve for the unknown rate of change. Usually it means substituting into the known, the information we know, just like the last couple examples we have done. So the first example we're given is on page 83 of your course notes. And it says the energy cost of a bird flight as a function of body mass is given by E equals 429 m to the negative 0.35 power, where m is the mass of the bird in grams and E is the energy expenditure in calories per gram per hour. Okay. Suppose that the mass of a 10-gram bird is increasing at a rate of 0.001 grams per hour. Find the rate at which the energy expenditure is changing with respect to time. So first, if we're given an equation already, right? So we could assume that we're going to use this equation and substitute in some of the information given. So they say that suppose that the mass of a 10-gram bird, so this is one piece of information, right, is increasing at a rate. That means derivative. So the mass is increasing at a rate of 0.001 grams per hour. So that would be that the change in mass with respect to time is 0.001, right? Because it says m is the mass of the bird in grams, okay? So that means the mass of a 10-gram bird. So that means our m is equal to 10. Okay, so that's the two pieces of information that we have to kind of derive from the given information. So find the rate at which the energy is changing with respect to time. So in other words, we are trying to find the change in energy with respect to time. That's what we're looking for, dE dt. So we would differentiate both sides of this equation with respect to time. So when we take the derivative of this function, remember 429 is just multiplied out front, so we can kind of just ignore that. When we find the derivative of an exponential function, right, we would multiply the exponent in front. So that would mean negative 0.35. And then we subtract 1 from the exponent, so negative 1.35. And then we would multiply by the derivative of our variable, dm dt. Okay, so this, we could probably put parentheses around all of that because that times a negative looks funny. Okay, so then we plug in what we know, right? So 429 is just a constant. We have negative 0.35 times m, they said was 10, to the negative 1.35, and then times dm dt is 0.001. Okay, so you definitely want a calculator for this. So dE dt in this equation is equal to negative 0.00067. And it said, find the rate at which the energy is changing with respect to time. Originally, it says it's calories per gram per hour. Now it's hours squared once we find the derivative of this. Okay, so this is our solution. Again, use calculator. Also, be careful if you're typing your answer in MyMathLab in the Pearson product. It generally, in blue letters below the box where you type your answer, it gives you instructions on how to type your answer. So it might say round to 3 decimal places or 2 or something of that nature. So be careful you read that. Okay, our next example. It says sociologists have found that crime rates are influenced by temperature. In a Midwestern town of 100,000 people, the crime rate has been approximated as C equals 1/10 times T minus 60 squared plus 100, where C is the number of crimes per month and T is the average monthly temperature in Fahrenheit. The average temperature for May was 76 degrees. So that, again, means T equals 76. It's not a change. It's just a straight up variable. And by the end of May, the temperature was rising at the rate of 8 degrees per month. How fast is the crime rate rising at the end of May? By the end of May, the temperature was rising at a rate of 8 degrees per month. Okay. So that means our variable T is the average monthly temperature. So the average monthly temperature was rising at 8 degrees per month. Now, I put a capital DT, so a derivative of the average temperature, over the derivative of just time in general. Okay, and that is equal to 8. So if we go back to our original equation that was given to us, 1/10 times T minus 60 squared plus 100, we are looking for How fast is the crime rate rising at the month of May? So that means we're looking for DC dt. Okay, that's what we're trying to look for. So if we take the derivative of both of these, remember 1/10 can just stay out front. First, you take the derivative of the outer function, so we would multiply by 2 out front, and then decrease the exponent by 1. And then we take the derivative of what's inside, so that would be dt with respect to little t. And the derivative of 100 is just 0. And so the next step is to plug in the information that was given to us. So 1/10 times 2 is 5. T was 76. And dt is 8. And if we plug that in and simplify it, we get 25.6. And of course, this is crimes per month. The change in the number of crimes with regard to time. Okay, next example. A 17-foot ladder is placed against a building. The base of the ladder is slipping away from the building at a rate of 9 feet per minute. Find the rate at which the top of the ladder is sliding down the building at the instant when the bottom of the ladder is 8 feet from the base of the building. Okay, so this one let's draw. Here's the wall, here's our ground. We have a 17-foot ladder placed against a building. So this length here is 17 feet. The base of the ladder is slipping away from the building at a rate of 9 feet per minute. 9 feet per minute. And now notice that's a change. That's a rate. Find the rate at which the top of the ladder is sliding down the building at an instant when the bottom of the ladder is 8 feet from the base. So we know this is 8 at some point, okay? We want to know the rate at which this is changing, okay? So let's call this distance x. And so the rate at which it's falling down the building will be dx dt. Okay, so what we will need to know is we'll use Pythagorean theorem, right? Because it's a triangle, it's a right triangle. The wall to the ground is a 90-degree angle. And so we can set it up like x squared plus 8 squared equals 17 squared. Now this, of course, doesn't include our x and our y. So we will have to find, I'm going to do this so that I can find what the distance of x will be, what the height of the ladder will be at the moment that we're 8 feet from the ground. So this just gives us the last piece of information we'll need when we actually find the derivative. Okay. I could have waited to do this, but it's probably easier to do it at the beginning. So as we solve for that, we will get x squared plus 64 equals 17 squared, 289. When we subtract 64, we get 225, so x is 15. And of course, we're going to ignore the negative solution because we're talking about a distance. So distances are positive. Okay, so now let's look at our actual equation. So if we're going to call this other distance, which we don't really need right now, y, this would be our horizontal distance. Then our general equation would say x squared plus y squared equals 17 squared, right? So x and y are changing, which is why we want to actually label them as variables because the ladder is slipping. However, the length of the ladder is not changing, okay? And of course, we could put 289. So if we take the derivative of this, we would get 2x dx dt plus 2y dy dt, and we want dx dt. That's what we're solving for. So we can plug in all of the rest of the information we found. So we found x is 15. We were given y is 8. Of course, we labeled that variable ourselves. The change in y with respect to time is 9. So if you solve this equation for dx dt, we get negative 4.8. So the ladder is sliding at negative 4.8 feet per minute. Okay, one more example for this section. It says a rock is thrown into a still pond. The circular ripples move outward from the point of impact of the rock so that the radius of the circle formed by a ripple increases at a rate of 2 feet per minute. Find the rate at which the area is changing at the instant the radius is 4 feet. So the radius of the circle from the ripples increases at a rate of 2 feet per minute. So the change in radius with respect to time is 2. Okay, so the area of a circle we know is A equals pi r squared. We want to know the rate at which the area is changing at, so that's per time. So we're looking for dA dt. So if we take the derivative of both sides, derivative of A is just dA dt. Pi r squared, well, pi is just a constant. It's just a number, right? So we can ignore it. So derivative of r squared would be 2r dr dt. And then we plug in the information given to us. 2 pi, we'll use our calculator for that. R, we want to know at the instant the radius is 4 feet. So we plug in a 4, and dr dt is 2. So finally, dA dt equals 16 pi, we'll just leave it like that, feet squared per minute. Okay, now it's feet squared because this is radius is in feet. If I backtrack it, so if I actually put in these units, this is 4 feet, and this was 2 feet per minute. So when we multiply that, we have feet and feet in the numerator and minute in the denominator. So that would be feet squared per minute.